Welcome to this SmartTechCheck EduSeries episode. I'm Mark Vena, CEO and Principal Analyst at SmartTech Research. I'll admit right up front that this is not our typical topic. We usually focus on market shifts, product strategy, AI, smart devices, and the technologies that shape mainstream adoption. Today, we are going deeper into the technical weeds because this topic matters. EV demand is rising fast, and that means the hidden systems inside the car need to evolve just as quickly. One of those systems is the onboard charger, or OBC. It is not glamorous, but it is mission critical. This EduSeries is based on a recent Infineon Technologies webinar conducted by Torsten Klemmer and Stefan Hanafiah, engineers in Infineon's onboard charger group. Their core message was clear. The industry cannot keep scaling EVs with bulky, expensive, old-school power conversion designs. Single-stage converters may sound like an engineering detail, but they point to a bigger shift. Fewer components, better efficiency, lower cost, flatter designs, longer life. In other words, this is not just about charging a vehicle. It is about making EV architecture smarter, leaner, and more ready for mass adoption. The first thing to understand is the scale of the shift. Infineon expects roughly 60% of global car production by 2031 to be electrified. Even more important, about 45% of global car production will need an onboard charger. That is a massive installed base, and it makes the OBC a strategic battleground. Torsten Klemmer made the point clearly in the webinar. Electrification is absolutely ongoing, and AC home and destination charging will remain dominant. That matters because home charging is where the OBC really earns its keep. The pressure on automakers is obvious. Consumers want faster charging, thinner vehicle platforms, better efficiency, and lower prices. Automakers want fewer parts, lower weight, higher reliability, and easier manufacturing. Those goals collide inside the power electronics stack. The old approach worked when EVs were still early adopter products. But as EVs move toward mainstream scale, every component has to justify its space, cost, and complexity. The onboard charger can no longer be treated as a utility box buried inside the vehicle. It becomes part of the value proposition. Smaller, smarter, and more cost-efficient is no longer optional. It is the price of admission. Here are 6 major forces reshaping the onboard charger. First, power is moving up. In the webinar, Infineon noted that 6.6 kilowatts is mainstream in China, 11 kilowatts is common in Europe and the Americas, and 22 kilowatts is becoming a clear trend. That means faster AC charging is moving from nice to have to expected. Second, battery voltage is climbing. 400-volt systems are mainstream today, but 800-volt architectures are getting serious traction, especially in higher-end EVs. Infineon even pointed to 900 volts and above coming into view. Third, bidirectionality is becoming more important. Vehicle-to-load and vehicle-to-home are already established in some use cases, while vehicle-to-grid is starting to gain momentum. Fourth, efficiency remains critical. Infineon referenced roughly 95 to 96% as state-of-the-art. But partial load efficiency still matters because vehicles spend a lot of operating time outside perfect conditions. Fifth, form factor matters. The industry wants flatter designs, especially in the Z dimension. Sixth, integration is accelerating. The OBC, DC-DC converter, and other high-voltage systems increasingly need to work together in one smarter box. That is the real story. EV charging is no longer just about speed. It is about system-level design discipline. Traditional two-stage architecture with power factor correction in top, this is where the architecture shift gets interesting. Traditional onboard chargers usually use a two-stage power conversion design. First comes power factor correction, or PFC. Then comes an isolated DC to DC conversion stage. That architecture is proven, familiar, and reliable. But it comes with baggage. You need bulky inductors. You need large DC link capacitors. You may need pre-charged circuitry. You also increase component count, board complexity, and potential failure points. Infineon's webinar framed the big question very directly. Does it always need to be 2 stages? Their answer was no. A single-stage matrix architecture simplifies the path. Instead of converting power through an intermediate stage, It creates a more direct AC to DC conversion flow. That sounds simple, but it is a big deal. It means eliminating bulky DC link capacitors. It means saving passive components. It means reducing weight and potentially lowering cost. This is the design philosophy shift. Stop adding more complexity to solve complexity. Start removing the unnecessary layers. In an EV, less is not just cleaner. Less can be faster, flatter, cheaper, and more reliable. The single stage advantage comes down to one word: simplification. In the webinar, Stefan Hanafiah explained that one of the key benefits of single stage topologies is the absence of bulky DC link capacitors. That means no pre-charge circuit, fewer passive components, and a cleaner overall design. That is not just an engineering win, that is a manufacturing win. It is a reliability win. It is a cost win. Fewer switches and smarter bidirectional switches can replace more complex switch banks. Eliminating electrolytic capacitors matters because those components can become weak points over time. A design with fewer parts has fewer places to fail. This is especially important as EVs move from premium products into higher volume, cost-sensitive segments. Automakers cannot afford elegant lab solutions that are too expensive or too hard to build at scale. The OBC has to become thinner, cheaper, more reliable, and still powerful enough to support evolving charging expectations. That is why single-stage architecture is compelling. It is not just a new topology for engineers to debate. It is a way to cut out the middleman inside the vehicle. In a market obsessed with range and charging speed, efficiency at the component level can become a competitive edge. The matrix converter is where this moves from incremental improvement to real structural rethink. Infineon's approach uses bidirectional switches on the AC grid side to create a more direct conversion path. Instead of relying on a bulky intermediate DC stage, the system manages power in a more streamlined way. In simple terms, you are taking a more direct route from the grid to the high voltage battery. That matters because every unnecessary conversion step adds size, heat, loss, cost, or complexity. In EVs, those penalties add up quickly. Stefan Hanafiah walked through several single-stage topologies in the webinar, including designs that behave more like voltage source rectifiers and others that behave more like current source rectifiers. The key point is that topology selection changes how the system handles filtering, switching, ripple current, and thermal behavior. This is not plug-and-play magic. It is hard engineering. There are trade-offs, including more complex PWM generation, AC filtering requirements, and questions around DC ripple current acceptance. But the potential upside is significant. A matrix converter can help automakers design flatter, more efficient, more integrated charging systems. That is why this matters. This is not a tweak. It is a power architecture reset. Now we get to the semiconductor choice: silicon carbide versus gallium nitride. Torsten Klemmer made an important point in the webinar. This is not about one technology being universally better than the other. It depends on the design target. CoolSiC is the robust veteran. Silicon carbide is proven, mature, and well-suited for high voltage, high temperature, high stress environments. Infineon points to scalable voltage classes like 750 volts and 1200 volts, which makes SiC highly attractive for demanding EV designs. CoolGaN is the performance pro. Gallium nitride can deliver lower switching losses and support higher frequencies. That can help shrink passive components and enable thinner, more compact designs. This is where the engineering decision becomes strategic. If the priority is ruggedness, voltage handling, and thermal durability, SiC has a strong case. If the priority is ultra-compact packaging and high-frequency performance, GaN becomes extremely compelling. For automakers, this is not just a component selection. It is a platform decision. The wrong choice can add cost, limit design flexibility, or create thermal headaches. The right choice can unlock a smaller, lighter, more efficient OBC. In EVs, the semiconductor is increasingly the strategy. Packaging is one of the most underrated parts of this story. Everyone loves to talk about silicon carbide and gallium nitride, but the package determines how much of that performance can actually show up in the real world. If you cannot move heat efficiently, reduce parasitic inductance, or save board space, the best semiconductor technology can get boxed in. Infineon's HD pack and QD pack packaging concepts speak directly to that challenge. The HDPAK half-bridge offers a dual-die half-bridge configuration, more than 15% board space savings, and 4 times lower parasitic inductance. That matters for efficiency, thermal behavior, and power density. The QD pack bidirectional switch takes a different angle. It uses a smart back-to-back configuration designed for native bidirectional power flow. That is especially relevant as vehicle-to-grid, vehicle-to-home, and vehicle-to-load use cases become more important. In plain English, this is about packing more power into less space without creating a heat problem. That is exactly what EV designers need. Flat matters because vehicle platforms are getting tighter. Efficiency matters because every watt loss becomes heat. Integration matters because automakers want fewer boxes, fewer parts, and cleaner assembly. This is the hidden layer where EV charging architecture either scales or gets stuck. The benchmark slide gives us a practical sense of where Infineon is aiming. The single-phase matrix target is around 7 kilowatts. The three-phase to single-phase configuration targets 11 kilowatts. The three-phase matrix converter targets up to 22 kilowatts. These are not random numbers. They map to the real charging world. 7 kilowatts fits residential level 2 charging. 11 kilowatts is highly relevant for more advanced home and commercial scenarios. 22 kilowatts points toward faster AC charging, where infrastructure and regulation support it. In the webinar, Stefan Hanafiah said Infineon's demo board is designed to investigate direct matrix converter topologies, both GAN and SiC bidirectional switches, Oryx microcontroller control, DC output ripple current, efficiency versus two-stage designs, and bidirectional functionality. That is the right mindset. This is not a victory lap. It is an engineering validation platform. The opportunity is real, but so are the challenges. Infineon called out issues like AC side filtering, higher DC ripple current, OEM acceptance, and complex PWM generation. That balance is important. The technology is promising, but it still has to prove itself under automotive realities. Even so, the direction is clear. EV charging wants to get flatter, faster, more efficient, and more integrated. So what is the bottom line? This Infineon webinar was technical, but it was also highly relevant. It showed that the future of EVs will not be shaped only by battery chemistry, charging networks, or software-defined vehicles. It will also be shaped by the power electronics buried deep inside the car. Single-stage converters are not a magic wand. Infineon was honest about the challenges, including filtering, ripple current, control complexity, and the need for OEM acceptance. That matters because automotive technology has to survive real-world cost, durability, safety, and manufacturing pressure. But the upside is compelling. If single-stage matrix architectures can reduce bulky components, eliminate DC link capacitors, lower BOM, improve reliability, and support flatter packaging, they could become a meaningful step forward for EV platform design. My balanced take is this. Infineon is not overselling a finished revolution. It is pointing to a practical architecture shift that deserves attention. That is why this topic belongs in a SmartTechCheck EduSeries episode, even if it is more technical than usual. The EV market is scaling, and the companies that solve the hidden engineering problems will shape the next phase of adoption. If you found this useful, please like, subscribe, repost, and share it. Also subscribe to the SmartTechCheck podcast on YouTube, and drop a comment with the topics you want Smart Tech Research to cover next. And for more insights into the future of electric vehicle mobility and onboard chargers, visit infineon.com/OBC.